Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 2 of problem set 8, orbitals and electron configurations. All right, number 6. Identify the number of planar nodes, radial nodes, and total number of nodes in the following orbitals. From that information, label each orbital with the appropriate shell and subshell values. Remember, shell is N, subshell is L, quantum numbers. All right, so if we have number of planar nodes and radial nodes, that'll give us total number of nodes. There aren't any other nodes that you need to know about, so just planar and radial. So letter A, if we look here, remember planar cuts right through the orbital, right through it. So you can kind of see one right here wrapping around, kind of separating the right from the left, okay? You can kind of see another one around the waist here, separating the top from the bottom. And then another one kind of right here, separating the front from the back. So that's a total of 3 planar nodes, cutting right through it, okay? I'll erase this so you can kind of see it better. Okay, so 3 planar. And radial, if there were radial, we'd see kind of other orbitals hovering around like this, and then we'd draw kind of one circling around it, but we don't see that, do we? So there are 0 radial nodes here. Okay, so that's a total of 3 nodes. 3 nodes total. Now, if you remember, total nodes is equal to what? N minus 1, which means nodes, or N, is equal to nodes plus 1. Okay, so if we're looking for the N, what type of shell this is in, we would just say this is N equals 4, right? Because that's 3 plus 1. And L, what's my L in this case? L is equal to 3. 3, because that's how many planar nodes I have. And when it was 3, we said it was what kind of orbital? It's an F orbital. So this is a 4F orbital, 4F. All right, letter B. Okay, you can kind of already tell they've kind of drawn in the planar nodes here for you, so it's kind of a giveaway. But that means there's 2 planar, so 2 planar. And let's zoom in to kind of see these radial here. So there's one kind of, you can kind of see this little d orbital here in the middle. Okay, that's separating, that's now being surrounded by another d orbital. So that's one radial node that's separating orbitals of different shells. And then here's another radial node. So that means we have a total of 2 radial. And then with the planar nodes, that's a total of 4 total nodes, right? 4 nodes total. So what does that mean? That means N is equal to 5, right? 4 plus 1 is 5, using this equation over here. So we know it's a 5, and then L is equal to what? 2, right? We have 2 planar nodes, which makes it what kind of orbital? A d orbital. And you can kind of already tell by the shape, right, that it's a d orbital, but just knowing the angular momentum quantum number also helps you to identify that. So this is a 5d orbital, 5d orbital. All right, letter C. You can kind of tell that this is cutting right through it right there. So that's going to be 1 planar node. Okay, and then I've got one kind of surrounding separating these orbitals here, and then another one separating those orbitals right there. So that's a total of 1 planar and 2 radial. Okay, and that's a total of 3 nodes. And that means N is equal to what? 4, using nodes plus 1. So when now I need to figure out L. So L is equal to 1, right? And we know that just because there's 1 planar. And well, when N is equal to 1, that's what kind of orbital? It's a p orbital. So it's going to be a 4p orbital, 4p. Okay, not too bad. Nodes help us a lot to figure out what kind of orbital it is, and especially what kind of shell it's in. All right, number 7. What is meant when 2 or more orbitals are said to be degenerate? All that means is they have the same energy. That's all you need to know. So, for example, we'll take the 2p subshell. Within the 2p subshell, you've got the 2px and the 2py and the 2pz orbitals. And they're just oriented differently, but they're all in the same subshell, which makes them degenerate, so they all have the same energies. Okay. So part B says, what orbitals are degenerate in a hydrogen atom? Okay. To be degenerate in a hydrogen atom, you have to have the same N shell. That's it. You don't have to have anything else the same. As long as you're in the same shell, you're going to be a degenerate orbital. Okay, so they have to have the same principal quantum number. Okay, that's all that matters in the hydrogen atom. Now that's different than every other atom. Okay, so part C says what orbitals are degenerate in all other atoms. In all other atoms, there are electron repulsion that occurs when more one plus electrons are present, right? So remember that they're both negatively charged electrons. If they come close to each other, opposites attract, and then those that are similar repel each other, right? So they start to repel each other. So we kind of have to have a different set of rules, because we're no longer talking about just one electron moving in the hydrogen atom. We're talking about several electrons moving within several different shells. And So what that means is you have to have the same N shell, so principal quantum number, and the same L subshell. So the example I gave you up here is actually an example of this, right? They were both in the same shell, which was 2, and in the same subshell, which was P. So they have to have the same N and L. So 3D, there are 5 orbitals in the 3D subshell. All 5 of them are degenerate with each other. Okay, in the 4p subshell, all three p orbitals in the 4p subshell are degenerate. Okay, but I would have to, it would be different for n, as given that you have to have the same principal quantum number. So n equals 3. You wouldn't have to designate which subshell it's in. Okay, the difference comes because of those electron repulsion. Okay, that's why there's the difference, is because now the electrons are repelling. Electrons are repelling each other. And that's really just the biggest difference between them. Just know that you'll have to have the same N and L subshell, okay, to be degenerate, to have the same energy. All right, number 8, write out the full electron configuration and the condensed electron configuration for the following atoms or ions. Okay, so what that means is we have to designate. Remember that this here in the periodic table is the S block, and this over here, right here, is the P block. Okay. And each period, these are each periods increased by one whole number integer. So we've got the 1 period, the 2 period, the 3 period, the 4 period, the 5 period, and 6 period, and then the 7th. Okay. Now, what's nice is that these periods correspond to n shells. So this is actually n equals 1, n equals 2, n equals 3, n equals 4, and so on. Okay, so when we're filling these out, we're filling out first the n equals 1 shell, and you'll notice that there's 2 electrons that can be filled, and that fills a 1s orbital. Okay, and then we get to here, we get a 2s orbital, and then it turns into a 2p subshell over here, right, where we have 1p orbital, 2p orbitals, and 3p orbitals. And hopefully this will start to make sense once we start to fill these in and designate where these electrons are going. So we've got atomic number 11. Okay, so I've got 11. Here's sodium. Okay. So I know that to get to sodium, I had to first put some electrons into the 1s orbital. And how many are there? 1, 2. Okay, so 1s2. Remember, there are only 2 electrons for every 1 orbital, right? But there are 3. Remember that there can be multiple orbitals in different subshells, right? So in the p subshell, we've got 3 different p orbitals. In the s subshell, we only have 1s, right? So then we go right, and then we start back to 2. So we've got that 2s, and this would be 2s2, right? We've got 1, 2 spots to fill in. Now we're going on to, this is now the 2p subshell. This is the p block, right? So this is a 2p. So I'm going to say 2p, and that's 1, 2, 3, 4, 5, 6. That's 2p6. Now careful, there are 6, but it's not in 1 orbital. That's in 3 different orbitals, okay? But there's just that's just what we have to do to signify this, okay? So 2p6, and now we're here at the 3s. Oh, 3s1, that's it. That'll be it for sodium. Now, to get the condensed form, all you have to do is go to the previous noble gas and write it in brackets. So if I were doing that, I would put neon, like this, and then 3s1. All that means is that we're assuming that it has the same electron configuration up to neon at that point, and then 3s1, okay? So this would be the condensed version of this. All right, so atomic number 17, where is that? Let's see, we've got chlorine over here. Let me go ahead and erase some of these notes here so we can kind of see better. Okay, so we got chlorine. So to get there, we had to go to get to the 1s, now the 2s and the 2p, 3s and 3p. So let me write these out, 1s2, 2s2, and then back to 2p6, right? That's what we had before. Now we're putting in both electrons in the 3s2, okay? And then we're now in the 3p, right? We're in the 3p, and we had to put in 1, 2, 3, 4, 5. We had to put in 5 to get there, okay? So this is going to be the full electron configuration, and now we have to go back to the previous noble gas, which happens to be neon again, to get the condensed version, and that would take care of all of this again. So we'd put neon, and then 3s2, 3p5. Okay, not too bad, right? Okay, and then atomic number 23, that's going to be vanadium right here, okay? So we had to go through the 1s, the 2s, the 2p, the 3s, the 3p, and the 4s this time, and now we're entering a new shell. Now, this block on the periodic table is what we call the D shell. Okay, this is where we start opening up D orbitals. Now, even though this is in the 4th period, this row of transition metals is actually in the 3D block, okay? We actually start with 3D when we're looking at the D block. So I would fill this in as 1s2, 2s2, 2p6, 3s2, right? Going right here, 3s2. Now 3p1, 2, 3, 4, 5, 6, okay? 3p6. And now 4s2, 4s2. And then we're going 1, 2, 3. That's going to be 3d3, okay? Kind of funky, right? It looks different. But this is the order that we fill these in. Because it just so happens that the 3D orbital is higher in energy than the 4s orbital. So that's why we do that. So if I wanted to do the condensed version, I just have to go back to the previous noble gas, which happens to be argon. So we're just going to put argon, which will get rid of all of this, okay? And we'll just say 4s2, 3d3. Now, sometimes what you'll see is professors will actually write this in chronological order. So you may see this written as argon, 3d3, 4s2, to put it in chronological end shell order. Honestly, to me, I don't think it's ever mattered all that much. Students really haven't lost points on it. But if your professor says one way or the other, obviously you should probably do that. All right. So now we're dealing with some ions on the bottom here. So we've got Fe2+. Okay, so I'm going to have Fe2+, but I'm 2 electrons short. So I'm actually going back to what would be the electron configuration for chromium. Okay, for chromium. But what I have to do first is fill it up to iron and then go back to, okay? And you'll see why we have to do it that way here in a second. So doing my typical filling in. So I got 1s2, 2s2, 2p6. Okay, so here's my 2s2, here's my 2p, 1, 2, 3, 4, 5, 6, 3s2. Oops, 3s2. 3p, 1, 2, 3, 4, 5, 6. And then 4s2, 4s2. And now we're getting into the 3D, 1, 2, 3, 4, 5, 6, 3d6, okay? But now I'm missing 2. I'm missing 2 electrons, right? Because I'm an ion. I'm the 2+ ion of iron. So what we have to do now is determine where we're going to lose the electrons. Now, it's going to be confusing, but D subshells don't like to lose energy. And in fact, you'll see that a lot of transition metals, when they create ions, they'll actually create either 1+ or 2+. Sometimes you'll see higher than that, but usually it's around 1+ or 2+, sometimes 4+. But the reason is because what we do is we actually get rid of the 4s orbital, because it'll actually take less energy for the atom to lose its 4s orbital than to lose its 3d6 orbital. And even on the subatomic levels of life, the atoms will do as little amount of energy as possible. Okay, they're just as lazy as us. That we don't like to do as much work. We'll do the least amount possible, and so will atoms. Right, they're going to do what costs them the less energy to do. And so losing the 4s orbital is more cost effective, and so we actually just erase this 4s2, and it just becomes 3p6, 3d6. Okay, and to write the condensed form of this, we just take care of this by writing the previous noble gas, which would be argon again, right? Argon. And then 3d6. Okay, so kind of funky. Some people will put will not use this principle correctly, and they'll end up putting something like 4s2 3d4, but that's not correct, because one of the reasons that this happens is because a half-filled D shell, right, with 5, if it was just 1, 2, 3, 4, 5 electrons, is more stable, and so it'll more readily lose the 4s orbital first. Then it will start taking them out of the 3D subshell if it needs to. Okay, all right. So copper 1+. We're going to be using the similar principle here. So we've got same electron configuration that we've been doing. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, now we're at copper now. Okay, so copper is what? 1, 2, 3, 4, 5, 6, 7, 8, 9 normally, right? So I'll put 3d9. Now, something to note here is back to this rule with this idea of stabilizing the D subshell. The D subshell wants to stabilize itself so much that if it's close enough, like at 9, it will actually steal an electron from the previous s orbital. So in fact, the way I've written it here is 4s2 3d9 is actually incorrect. The way you would actually write this, if this was regular copper, okay, no, I haven't done the ion yet, so don't worry about that. Then you would write 4s1 3d10. okay, 3d10, because having a filled D subshell is more cost effective for the atom than having a full S subshell. Now, it's kind of easy. The reason we show it this way first is because now it's easy to tell why it becomes a 1+, because it's really easy to lose that 1 electron from the 4s orbital. So all we do is erase the 4s, and then this just becomes the 3d10. Now, to write the condensed version of this, right, you just write argon, and then 3d10. Okay, not too bad, right? Not too shabby. All right, last one, Br minus. Okay, Br minus is way down here. Okay, it's in the, let's see, the 4th period. Okay, so we're going to do the 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then we've got the 3d10 now. We've filled in all these now, and then we're going to 4p, and then we're going to 1, 2, 3, 4, 5. Okay, 5. But it's got an extra electron, right? We're at Br minus. So now I have to add one more to that P subshell, and this becomes 4p6. Okay. So to condense this down, what you would do is just take the bottom here, go to the previous noble gas, which is still argon here, argon, and then 4s2, 3d10, 4p6. Again, you may have professors that ask you to do it this way, argon, and then 3d10, 4s2, 4p6, because the reason we sometimes do that is because it's easier to see the valence electrons. Valence electrons are the electrons that are in the outermost shells. Okay, so in this case, we'd have 8 electrons, 8 valence electrons. And we wouldn't really pay attention to this because it's technically in a lower shell. It's in a lower shell. And so these ones are the ones that are acting as valence shells. So that's kind of why they have you write it like that sometimes, but it's not necessarily all the time that they'll ask you to do that, okay? But that will be your answer, okay? Hopefully that writing out electron configurations like that made sense. All right, so what ions are the first 3 atoms listed in the previous question most likely to form, if any? Okay, so let's look at these 3. And the key is looking at the very last orbital, okay? On atomic number 11, what you want to know is that every atom wants to get to what's called the perfect octet, okay? And the octet is having 8 electrons in its valence shell, okay? Remember, I was saying valence here. Valence is the shell that's the outermost shell, or the one in the highest principal quantum number of the atom, okay? So what you have to do is look at the valence shell and determine, is it going to be easiest for this to gain 7 electrons to get that octet, or lose 1 electron to get that octet? And especially for the S block, you're always going to lose the electrons because it's easier to lose 1 electron than it is to gain 7. Okay, and I can tell that because there's only 1 electron in the valence shell in this 3s orbital. So for atomic number 11, so I'm going to say atomic number 11, it's going to be a 1+, 1+ ion, because if it loses this electron, that means it lost a negative, and so it becomes a 1+. Okay. So that's for atomic number 11. Now for atomic number 17, so atomic number 17, let's look at the valence shell. Okay, so the valence shell is 3s2, 3p5. Okay, so how many valence electrons is that? That is 2 plus 5, that's 7. Okay, now is it easier for that to gain 1 to get to 8, or to lose the 7 to get to positive 7, right? And the easiest obviously is to gain just 1. And so it's going to be -1. -1 type of ion. And you could say this is just a cation. Cations are just positively charged, and anions. Okay. And then last one, atomic number, let's see, is it 23? I think it's 23. Yeah. Okay, so 23, we had vanadium. Okay, now vanadium, what was the valence shell? The valence shell, this is kind of hard to tell, because a lot of times people will say, oh, well, it's the S or the D. But remember that most transition metals will be likely to lose the electrons from the 4s orbital more than it will from the D subshell. So this one is most likely to form, because this now becomes kind of the outermost electrons. It'll most likely now form 2+ mostly. Vanadium can form other types of cations as well, and you'll notice that some of the ions, like I was saying before, can have 2+, 1+, or 3+ and 4+. But you'll notice that there are patterns with the D subshell with those 3+ and 4+ as well. Okay, but we just won't cover those right now. All right, cool. So number 10, the last one for this part. Which of the following configurations depicts an excited carbon atom not in its ground state? So the key here is knowing how we fill these in to start with, and that if any electron is in a higher energy level, then it's considered excited. So hopefully that'll make sense as we go through these. So 1s2, 2s2, 2p2. Okay, so 1s2, I've got 1s2, 2p2, or 2s2, and then 2p2 here. Okay, now this is actually a grounded carbon. So this is not excited, so it's not going to be A. So grounded carbon. So it's in the lowest possible energy. Okay, so this is just not going to be the one for carbon. Now, if we go to part B here, or option B, it says 1s2, 2s2, so 1s2, 2s2, and then 2p1. Ooh, that's still a ground state, and it's actually not even for carbon. That's a grounded boron. Grounded boron. Okay, so this is not carbon in an excited state yet. All right, so letter C, we've got 1s1 or 1s2. So 1s2 and then 2s2. And then 2p1. Okay, 2p1. But then we jump up to 3s2. Ooh, that's weird. So let's figure out how many electrons carbon was supposed to have. So it was supposed to have 1, 2, 3, 4, 5, 6. Okay, so this one has 2, 4, 6, 7. So it's not even the right atom at this point. So let's just stop there and not even worry about the rest of this, because too many electrons. There are too many electrons for carbon. All right. Letter D here says 1s2. Let's go ahead and erase some of these X's here. 1s2. All right. 2s2. 2p1. Okay, 2p1. We got 2p1. Similar to last time, except now we got 3s1 up here. Okay. So how many electrons is carbon supposed to have? It's supposed to have 6, right? So that would be a total of 2, 4. Yeah, that's 6. Okay, so that's valid so far. And it looks like 1 was right here, but then it jumped up to a 3s orbital. So yeah, this is totally an example of that. We'll eliminate, see if we can eliminate E, or if it's going to be another one here in a second, okay? But so far we can tell that this is going to be an excited carbon. So this is excited carbon. Okay, so it had the right amount of electrons. And as filling them in, we could tell that, okay, one of them jumped up from the 2p to the 3s. Okay, so it's in an excited state, not in its ground state. All right, last one, 1s2, so 1s2, 2s2, and then 2p4, 1, 2, 3, 4. That's too many electrons, right? We're only supposed to have 6 here. This is 8, so too many again. All right. Well, I hope that was helpful for electron configuration. Sometimes they can be a bit complicated, as well as for nodes. Hopefully that was helpful in determining what kind of orbitals and shells and subshells we'll be having. We'll see you in part 3.